This video discusses the quotient rule of differentiation. During the first half of the video, I will discuss the proof of the quotient rule, and after that, we will look at 3 worked examples. Here's the quotient rule. We will let f, g be differentiable functions and g is not equal to 0. We will let y be f over g. We will let y prime, f prime, and g prime be the first derivatives of y, f, and g respectively. Then the quotient rule says the derivative of y prime is equal to g times f prime minus g prime f. All of that has to be divided by g squared. Please note that when y is defined as f over g, where f and g are differentiable functions and g is not equal to 0, the first derivative of y prime, is equal to g times f prime minus g prime f divided by g squared. Now we will look at the proof. For the proof, I'm going to use the first principles. For those who need help on first principles, there's a separate video explaining all the details of that. So in this video, I'm not going to introduce the first principles. Instead, I'm going to go ahead and directly use the first principles. So here's the proof. We're going to let h of x be f of x divided by g of x. Then from that, we have h of x plus delta x to be equal to f of x plus delta x divided by g of x plus delta x. Now, from the first principles, we can go ahead and write down the right-hand differentiability. The equation is d plus x equals x. I'm going to write down the generic equation. We know that this is equal to limit as delta x approaches to 0. On the numerator, we're going to have h of x plus delta x minus h of x. All of that's divided by delta x. In the context of this problem, we have defined h of x as f of x over g of x and h of x plus delta x as f of x plus delta x over g of x plus delta x. So I'm going to go ahead and replace those two things in this right-hand differentiability equation. D plus at x equals x, this should be equal to limit as delta x approaches to 0. This delta x term in the denominator, for simplicity, I'm going to write it as just 1 over delta x times all of that numerator separately. Therefore, let me write 1 over delta x first. I will open brackets. Now I'm going to write h of x plus delta x, which is f of x plus delta x divided by g of x plus delta x. That minus h of x. H of x is equal to f of x divided by g of x. Close brackets. Now we need to simplify this. How would you simplify that? In order to simplify this part, we are going to need a common denominator. We need a common denominator means this first fraction, both top and bottom, should be multiplied by the other denominator, which is g of x. And similarly, for this fraction, both top and bottom, should be multiplied by the other denominator, which is g of x plus delta x. So let's go ahead and do that. This is now equal to limit as delta x approaches to 0. There's this 1 over delta x. I will open brackets. First term is f of x plus delta x over g of x plus delta x. We need to multiply both top and bottom by g of x g of x for the numerator and g of x for the denominator. By doing so, I'm not changing the problem given. Minus, the next term is f of x over g of x. That has to be multiplied by g of x plus delta x over g of x plus delta x. So what I just did was just like multiplying each of these two terms by 1. We did that to have a common denominator. Simple college algebra. Now all of this is equal to limit as delta x approaches to 0, 1 over delta x, open brackets. Let me write down this common denominator as just one denominator for all of these. Here's that denominator, g of x plus delta x times g of x. The denominator times, when I look at this first part, I have f of x plus delta x times g of x. Let me write that down, f of x plus delta x times g of x. And we have minus f of x times g of x plus delta x. I will close the brackets. Now, as it is, there is nothing much that can be done. Therefore, I need to do a modification for this. So here's the modification I'm planning. This is equal to limit as delta x approaches to 0, 1 over delta x, brackets, the denominator stays as it is. The first term of the numerator is f of x plus delta x times g of x. And then I'm going to do a small modification. I'm going to add a quantity and subtract the same quantity. In fact, I will start by subtracting a certain quantity. So the quantity I'm going to subtract is minus f of x times g of x. Then, to have no change, I must also add the same quantity. Therefore, let me plus f of x times g of x. And finally, I have this minus f of x times g of x plus delta x term. Let me write that down. Minus f of x times g of x plus delta x. All of that has to be divided by g of x plus delta x times g of x. Let me close the brackets. Now this is equal to limit as delta x approaches to 0, we have 1 over delta x, open brackets. The denominator stays as g of x plus delta x times g of x. So let me write that down, g of x plus delta x times g of x. From the numerator, I'm going to group this first part, the first two terms. From those two terms, you can clearly see that gx can be factored out. So let me go ahead and factor out gx. When I factor out a gx, let me open brackets. The first term is going to be equal to f of x plus delta x. And there is this negative symbol. Let me write that down. From that second term, when g of x is factored out, we have f of x remaining. Let me close the bracket. And now I need to focus on these next two terms. From those next two terms, I have an f of x as a common factor, which can be factored out. However, right here in the middle, there is a plus sign. Instead of that plus sign, I'm going to factor out a minus f of x. From those last two terms, when I factor out a minus f of x, let me go ahead and open brackets. I will look at this last term first. That last term has a minus f of x times g of x plus delta x. Minus f of x is already factored out. Therefore, I'm going to write it as just positive g of x plus delta x. Therefore, this first term becomes g of x plus delta x. Now if I look at this first term, it is a plus f of x times g of x. What we factored out was a negative f of x. From positive f of x times g of x, if negative f of x is factored out, what's remaining? That should be a negative g of x, because negative f of x times negative g of x is equal to positive f of x times g of x. Let me write that down. The next term is minus g of x. Let me close this bracket. Let me close the other bracket as well. Now I'm going to split these two fractions. This is one fraction and this is another fraction. Those two are separated by this negative symbol in the middle. So let me split that one fraction as two fractions and rewrite. When I rewrite as two fractions, I will put this delta x also in the denominator for each of those two fractions, because that delta x term is factored out as 1 over delta x, which means delta x is in the denominator. When I rewrite all of that, this is equal to limit as delta x approaches to 0. Here is the first of the two fractions. I have a gx and bracket f of x plus delta x minus f of x. In the bottom, I'm going to have a delta x and also g of x plus delta x times g of x. And after that, I have this negative symbol. Let me write that down. Minus, I have f of x on the numerator, bracket g of x plus delta x minus g of x. Close the brackets. In the bottom, I will have delta x times g of x plus delta x times g of x. Close the big brackets as well. The meaning of the big bracket outside like this is that I need to consider delta x approaches to 0 with all the terms inside. So when I look at this first fraction, just focus on this part inside the brackets, f of x plus delta x minus f of x, along with divided by delta x term in the denominator. We know that delta x approaches to 0. When that happens, what can you say about that highlighted part? As delta x approaches to 0, f of x plus delta x minus f of x divided by delta x is the first derivative of f of x according to the definition of the first principles. And for the rest, I can directly substitute delta x approaches to 0. So let me do that part first. This is therefore equal to, I have a gx and I have the first derivative of f of x, which I write as f prime x, and then from these two terms, when delta x is equal to 0, it's going to be g of x times g of x, which will be simplified to become g of x squared. Then I have this negative symbol minus. Once again, I need to focus on limit delta x approaches to 0 and this highlighted part from top and bottom, g of x plus delta x minus g of x, all of that's divided by delta x. That part, as delta x approaches to 0, should be equal to the first derivative of g of x as per the definition of the first principles. Then for the rest of that function, I can substitute delta x equals 0. When I do that, of course, this term is gone. Then it becomes g of x squared once again in the denominator. There is no change for this first term. It stays as f of x. So let me write down those pieces. It will be f of x times g prime x divided by g of x squared. This actually completes our proof because we have the same denominator. We can write it as just g of x everything squared as one denominator, and then first term is g of x times f prime x minus the second term is g prime x times f of x. In short, we wrote it down this way. When you have y equals f over g, we said y prime should be equal to g times f prime minus g prime f. All of that's divided by g squared. When you write it like this, we are not specifying the variable. When you write it this way, we have specified that the variable is x. Alright, so that's a complete proof of the quotient rule. Now we will look at a couple of examples. Here is your first example. Let's say y equals 3x plus 1 divided by 2x plus 5. Find dy by dx. This problem, of course, has a numerator and a denominator, which means we must use the quotient rule. Let me rewrite this problem as given. Y equals 3x plus 1 divided by 2x plus 5. We are going to need an f and a g. So we will consider all of this numerator as f and all of this denominator as g. So right here we have f, right here we have g. As soon as you identify f and g, we will also need f prime and g prime. F prime should be equal to the derivative of 3x plus 1. When you differentiate 3x, it's going to be equal to a 3. When you differentiate 1, it's equal to 0. When you differentiate the denominator, we get g prime. That should be equal to the derivative of 2x plus 5, which is equal to 2. Now we can write down the answer. We know dy by dx, or y prime for simplicity, should be equal to g times f prime minus g prime f. All of that's divided by g squared. We simply have to substitute these values. On the numerator, we will have g times f prime. G is equal to 2x plus 5. F prime is equal to 3. So the first term is 2x plus 5 times 3 minus the second term is g prime f. G prime is equal to 2. F is equal to 3x plus 1. Therefore the second term will be 2 times 3x plus 1. All of that's divided by g squared. G squared should be equal to 2x plus 5, everything squared. Now you need to simplify this. From that we get dy by dx equals 3 times 2x is 6x, and minus 2 times 3x is another 6x. Those two 6x's will be cancelled. 3 times 5 is 15, minus 2 times 1 is a 2. So on the numerator we have just a 13. That's divided by 2x plus 5, everything squared. That's the answer for that problem. We will look at another example. Here is your second example. Let's say we need to differentiate tangent x. During one of our previous discussions, we saw how to differentiate tangent x using the first principles. However, if you use the quotient rule, the life is easier. We know that tangent x can be written as sine x over cosine x. We will label the numerator as f and the denominator as g. Then f prime should be equal to the derivative of sine x. Using the first principles, we proved that the derivative of sine x is equal to cosine x. And then I need g prime, the derivative of cosine x. Using the first principles, we proved that the derivative of cosine x is equal to negative sine x. Now we can write down dy by dx. Dy by dx, here's the generic equation, g times f prime minus g prime f. All of that's divided by g squared. Now I need to write down g times f prime. G is cosine x times f prime is also equal to cosine x. When those two are multiplied, we get cosine squared x as the first term on the numerator. Cosine squared x. And then I have this minus sign. With that, I need g prime times f. G prime is equal to negative sine x times f, and f is equal to sine x. Therefore, g prime times f should be equal to negative sine squared x. It's always safe to write negative numbers or functions inside parentheses. It's negative sine squared x. All of that has to be divided by g squared. Since g is equal to cosine x, g squared is equal to cosine squared x in the denominator. Now we need to simplify. Dy by dx should be equal to, on the numerator, what do you have? Once you simplify this numerator, the first term is cosine squared x, and then I have a negative symbol right here, and it has to be distributed to the minus sign right there. Those two will simplify to become a positive sine squared x. In the bottom, I have cosine squared x. What is cosine squared x plus sine squared x? That's the first Pythagorean identity from trig, and that's equal to 1. That's divided by cosine squared x. We may do some further simplifications and write down dy by dx as equal to, what is 1 over cosine x? We know 1 over cosine x is secant x. Therefore, 1 over cosine squared x should be equal to secant squared x. Therefore, this is equal to secant squared x. Please remember this result. It's a very important result. What we just proved was the derivative of tangent x. That's equal to secant squared x. Please note that using the quotient rule, you can also find the derivative of cotangent x and also secant x and cosecant x. Now we will go on to another example. Here is your third example. Let's say y equals x squared minus 5x plus 6 divided by 3x plus 1. Find dy by dx. Or in other words, find the first derivative. Just like earlier, we need to identify f and g. I will let the numerator be f, the denominator be g. Very straightforward. F prime should be equal to 2x minus 5. From the denominator, g prime should be equal to 3. Now we can write down dy by dx. Dy by dx, generic equation is g times f prime minus g prime f, all of that's divided by g squared. Then dy by dx should be equal to, on the numerator we have g times f prime. G is equal to 3x plus 1. That times f prime, which is equal to 2x minus 5. That minus g prime, which is equal to 3, times f. F is equal to x squared minus 5x plus 6. All of that's divided by g squared, which should be 3x plus 1, everything squared. Now you need to simplify this. When you simplify that, it becomes dy by dx equals, on the numerator we will have 6x squared minus 3x squared, which is a 3x squared, and minus 15x plus 2x plus 15x, which will be simplified to become a positive 2x, and then minus 5 minus 18, which will be simplified to become minus 23. In the denominator we have a 3x plus 1 everything squared. Try to simplify as much as possible with these kinds of problems, especially if your numerator and also denominator are polynomials. Then you can always completely simplify and keep a nice answer like this. However, there are some situations where further simplifications may be a little bit tedious. In such cases, we may stop right after showing the differentiation. We will look at an example. Here is your fourth example. Y equals x squared times tangent x minus 3x plus 2, all of that's divided by 2x plus 5. Differentiate this function and obtain dy by dx. So let me take this as the function f and this as function g. Then we need to find f prime and g prime. G prime is very straightforward, but how about f prime? Please note that the first term right here is a product between two functions of x, which means you must use the product rule when you differentiate that part. So I'm not going to revisit the product rule at this point. There's a separate video explaining all the details of the product rule. You are expected to know the product rule before working on this problem. For those who need help on product rule, I'll have the link posted down below in the description. Here I'm going to directly apply the product rule. Therefore, f prime, or the first derivative of the function on the numerator, should be equal to, we know according to the product rule, it's one function times the derivative of the other function plus the other function times the derivative of the first function. So it'll be x squared times the derivative of the tangent x, which is secant squared x, plus tangent x times the derivative of x squared, which is 2x. It's preferred to write 2x before writing that tangent x rather than after tangent x, to prevent any confusions regarding whether this x associated with tangent x has to be multiplied with 2x or not. When you write it this way, absolutely that 2x has to be multiplied by complete tangent x rather than tangent of x times 2x. Alright, and then I have a minus 3x. When you differentiate that, it becomes a minus 3. Similarly, we can write down g prime. What is g prime? G is equal to 2x plus 5, therefore g prime, the first derivative of g, should be just equal to 2. Now we can write down dy by dx, or the first derivative of that given function. We know it's going to be g times, which is 2x plus 5, times the first derivative of f, which is f prime. Let me write down all of this as f prime. X squared times secant squared x plus 2x times tangent x minus 3. That minus g prime times f. G prime is equal to 2. That times f is equal to x squared times tangent x minus 3x plus 2. All of that has to be divided by g squared, which is 2x plus 5 squared. This problem can also be simplified a little bit further. For example, when you multiply the 2x with 2x tangent x, you know it becomes a 4x squared tangent x. And with that, there's this minus symbol, and 2 times x squared tangent x term is there. Those two can be simplified. However, for a problem like this, you can simply keep this as your final answer. I will not take any points off. Alright, I'm going to stop the video on the quotient rule of differentiation at this point. Thank you so much.